So good afternoon, everybody. কার কি হয়েছে বলো এবার। We decided last week to go through some particular topics on potential flow up to, I think, if I can remember, up to the basic flow patterns. And based on that, we can have some discussion. So I can just go through a very quick summarization of what are those topics which were actually discussed already through video lecture, as well as in the notes you have seen probably. So basically we started with the basic assumptions of ideal fluid flow, potential flow, and based on that the governing equation can be framed, which I think you have already seen, that ultimately it leads to this form, half rho v square plus p is equal to constant. So this is the form which can be obtained using the different assumptions, particularly I think this rotationality condition, that is curl of the velocity equals to 0. And from the inviscid condition, we can drop the viscous term in our Navier-Stokes equation. So the left-hand side, that is the inertia term and the pressure gradient term, those will be left. I mean, and if you then integrate that particular equation, we get this form. It is actually, if P is the static pressure, it can be also written in terms of piezometric pressure form, because this will remain valid actually if the plane of flow, that is the XY plane, may not be horizontal, then also it is applicable. Only thing is that you need to incorporate the elevation term, and that could be very well incorporated by mentioning P instead of, I mean, by mentioning this P as P star, and this P star is nothing but your P plus rho g z. Okay, so this is the additional term which comes inside this P star. So if it is written in this form, then it will remain valid for any kind of orientation of the plane. Otherwise, if you only write half rho v square plus p is equal to constant, it is actually valid for horizontal plane, so to say. So that is the starting point. I mean, and that is actually leads to the our very familiar form of the governing equation, which we know as the Bernoulli's equation. So in potential flow, it is actually the Bernoulli's equation which is applicable, and it is obvious because if you look into the assumptions, incompressible, inviscid, any rotational, while deriving the Bernoulli's equation from a different approach, perhaps you came through these different assumptions and dropping one by one term to arrive into the same form. Okay, so then I mean, after with this understanding, we actually proceeded towards defining the two functions, which are stream function and velocity potentials. The first one, stream function, actually is the direct consequence of continuity equation, and which is denoted by psi, and it is actually the very definition comes from satisfying the continuity equation, incompressible flow continuity equation, of course, that is del u del x plus del v del y is equal to 0. So you need to satisfy this. And so the way this particular function is being defined, inherently it satisfies the continuity equation. So, and then actually, if we apply the irrotationality condition, then we get the form which is known as the Laplace equation. That is del square psi is equal to 0. Okay. And we had some discussion on this stream function, the very characteristics of this stream function. It is a point function. It depends on the point, and the physical significance of stream function, and the relation of stream function with the stream line, actually. And that is very important because actually in your fluid mechanics 1, you had the definition of streamline. And from that definition, I hope you have also gone up to the derivation of the equation of streamline. And here, by stream function approach also, we can lead to another representation of the streamline where the stream function remains constant, right? So that also has been discussed. I mean, where by defining d psi, that is this d psi as a composition of that del psi del x dx plus, and we can write del psi del y dy. Okay, and by the definition of this, the velocity components u and v, we can write this as v dx minus u dy, because u is defined as minus del psi del y and v is defined as del psi del x. So, and also we recall the equation of streamline where you have dx by u is equal to dy by v. So, recalling that equation and then putting it into this form of d psi, we get d psi equals to 0. And that indicates that this stream function, if d psi is equal to 0 on a streamline, that indicates your stream function will remain constant. And that is also termed as equation of streamline. Okay. And then we had the physical significance. Actually, stream function is one representation of the rate, mass flow rate, you can say, in some form. The index or the value of the stream function is one kind of representation of this mass flow rate. As it is a point function, so in a flow field, as the number varies, because along a streamline is a constant, so you can choose any reference. It could be the origin, or I mean, in physical manner, it could be that location where you may have your velocity 0. That is, it may be on the boundary where you have 0 velocity and 0 flow rate. As you go normal to the direction of flow, your cross section goes on increasing, and thereby your flow rate gets increased. So that is the physical situation. What happens? So in case of a stream function, actually, the same thing is being represented by just a minute. So, I mean, what are you saying that if these are the streamlines of a particular flow, mm, so as you encompass more number of streamlines, you will be having more amount of flow rate, isn't it? So, uh, we had the concept of the stream tube, right? So each and every streamlines are having a particular value of psi, maybe psi 1, psi 2, psi 3, something like that. So these values are actually uh, reference value, you can say, with respect to uh, data. So this particular point where you may have chosen your, or I mean, instead of this, it will be better to understand. So this point where you have chosen psi is equal to 0. So psi 1 may be some value as equal to, say, 1, then this will be 2, 3, 4, and so on. So this 1, 2, 3, 4 is basically with respect to psi equals to 0. Maybe at psi equals to 0, you are having a particular known flow rate, or it is really, it may be 0. That means if it is at the boundary. Okay. So as you go in this direction, you are having increase the value of the stream function representing more amount of flow rate occurring through it. And it doesn't matter in which direction you actually, I mean, in which path actually you are going from, say, A to B. So these are the two end points. So you may go through this direction, through this path, you may go through this path. So as this, the value of the stream function only depends on the point on a particular flow field. That means this point as well as this point, both are having same stream function value, as both this point is residing on a same streamline. That is important. Okay. However, these 2 points, this point and this point, will be having again the same stream function value, but it is not same with the rate cross. I mean, these two are not going to be the same stream function value. Okay, so it should be on the streamline. So those I mean are being also discussed in our physical significance part of stream function. And then from that approach also, we had the definition of stream function and its relation with the velocity vector, and also the sign convention. That is important. The sign convention, basically in some text you may find the relation of these two velocity u and v with the stream function, as well as later in the velocity potential, with a different sign than the one that I have used in this material. Okay, so my point is that in some text you may find u as equal to del psi del y instead of minus del psi del y, and v may be as minus del psi del x, right? So I mean, there is no such mistake in any one of the text that you may come across. But the thing is that you need to follow any one of them. You need not. You should not mix between the two type of sign convention. If you are following the one that I have described in the material, then with that sign convention, the definition of velocity potential will be consistent. Otherwise, if you are following a different sign convention and you are, say, defining velocity potential as del phi del x as u and del phi del y as v, that may end up with a different result in the some problem that you may be solving. Okay. So if you are using the definition of u and v in terms of psi as minus del psi del y for u and del psi del x as v, then the definition for velocity potential should be minus del phi del x as u and minus del phi del y as v. Okay, so that this set of the definitions remain consistent. The other set is u is equal to, you may have del psi del y, and v is equal to minus del psi del x. In that situation, you should define u and v as del phi del x and del phi del y. Okay, no need to incorporate minus. So the treatment in the book Massey, actually, I mean, that is another reason of defining the velocity potential is that, I mean, as you go in the direction of flow, your potential decreases. That's why this minus sign arises. Okay, so the velocity potential decreases in the direction of flow. That is the logic that coined by Massey in his book. So that is another reason. Okay, so I mean, like stream function, the very definition of velocity potential comes from the to satisfy the irrotationality condition. Instead of the continuity equation, to satisfy continuity equation, the main purpose of velocity potential is to satisfy the irrotationality condition. So by satisfying that, inherently, we have the definition of this function, velocity potential, and it is also a point function. And then if you use it in continuity equation, incompressible continuity equation, of course, then again you end up another Laplace equation, that's where phi is equal to 0. So these two functions actually mathematically indicate they are both are linear, and as these two functions are linear, mathematically you can add up different functions, the same different types of these velocity potential functions or different types of the stream functions. So the method of superposition is valid if you treat a particular fluid flow problem. Of course, should be satisfying the assumptions of ideal flow. Then in a very straightforward, easy manner, you can add different functions and end up with a particular flow pattern that we will see later after having the understanding of the basic flow patterns. So that is one of the reason why, instead of having this UV form, the potential flow, the ideal flow, is dealt with the two functions mainly, either stream function or velocity potential, because these two functions are correlated between themselves by means of, in the next part, it is also being shown that these two functions means the lines where these function values are constant, typically streamlines for stream functions and equipotential lines for velocity potential. So, I mean, like these stream functions, we can have velocity potential lines like this, which are, series of these lines where you can have phi 1, phi 2, and phi 3, where these corners between the respective two lines, the stream lines and the equipotential lines, this corner will be 90 degrees. That actually, because these two functions are perpendicular or orthogonal to each other. So that is why if the pattern of the streamlines of a typical flow is the one which I have drawn, then one can expect to have the velocity potential lines like this. So these lines, phi 1, phi 2, phi 3 are called velocity potential line, or or these are also known as equipotential lines. So we have these equipotential lines, we have the streamlines. Already we had the definition of streamlines in our fundamental fluid mechanics, and here also. So these are the streamlines where you have psi constant, and the equipotential lines are the lines where we have psi constant. So a particular flow field can be represented by having the network of the streamlines and equipotential lines, which is also denoted as flow net, right? So after having these two functions defined, we can have the flow net, definition of flow net as well. Okay. So that is valid for 2D rotational flow, because see, streamlines, stream functions are the stream functions can exist for rotational flow as well, because the very basis of stream function is the satisfaction of continuity equation. Right, but velocity potential only it will exist for rotational flow. Why? Because you see, the very introduction or the definition of velocity potential lies in the fact that you have to satisfy rotationality condition. So that means it should be rotational flow. So if it is a rotational flow, you are not going to have the definition of velocity potential to be satisfied. So that is why also this the flow, rotational flow, is also known as potential flow, because the function velocity potential will exist here. Okay. So in order to have this flow net, you need to have a 2D rotational flow, and of course inviscid, incompressible, and so on. So this series of lines actually is known as, which forms a network, is known as a flow net. Okay. So that is basically the way stream function and velocity potential function have been defined, and then we moved into this another very important aspect of potential flow, that is the definitions of circulation, vorticity, and velocity. This circulation and vorticity. In our introductory discussion, we had this definition of circulation and vorticity. Here again, actually, we define the circulation. Yes. Yes.
Sir, বলছি ল্যাপ্লাস ইকুয়েশন কোন ফাংশন যদি স্যাটিসফাই করে তাহলে ওটা কি স্পেশাল কিছু ডিনোট?
ল্যাপ্লাস ইকুয়েশন যদি স্যাটিসফাই করে, এটি প্রশ্ন তোমার? হ্যাঁ, সেটা আমি বললাম তো, যে ল্যাপ্লাস ইকুয়েশন স্যাটিসফাই করছে মানে ফাংশনটা লিনিয়ার।
যদি কোন ফাংশন 0 হয়,
হ্যাঁ,
মানে ওটাই বলছি, ওটা কারণটা কি?
কারণটা কি বলতে, মানে কোনটার কারণ?
ওই ল্যাপ্লাস ইকুয়েশনের del square psi equals to 0.
Del square psi equals to 0. That actually by the way you have defined stream function or velocity potential, and with the conditions of the flow, mathematically,
ওইটা বুঝতে পেরেছি,
হ্যাঁ,
জিরোটা বুঝছি। আচ্ছা
ঠিক আছে। Actually, I have not get your
Yes.
query. Anyway, I think you have got your answer or you have understood. So shall I continue? So in the next part, actually, we moved into circulation and vorticity, where circulation is defined in a mathematical, where circulation is being defined in a mathematical manner. That is basically, it's a line integral of, from Stokes' theorem, it's a line integral of tangential component of the velocity taken around a closed curve or a closed loop, okay, in the flow field. So that means, say you are having this as a flow field, and flow field means these are the streamlines. So if circulation, if you want to find out, you need to have a closed contour or a closed loop. That means something like, or let me draw in this way, something like this. Okay, so circulation can be defined for this closed form that I have drawn by red line, which may consist of, say, this stream line having stream function psi1 and the stream function psi2, or maybe psi3. Okay, and these two additional lines to make this a closed loop. So you need to have circulation as cyclic integral for the velocity and along the line dl. Okay, so it's a line integral to be taken around a closed curve. So what we have seen that for an elementary cross section, delta x, delta y size, if you do this very routine exercise by having the two velocity defined and having their gradient in the respective directions, so you can get a particular form of circulation which contains two terms. One is del v del x minus del u del y, and one delta x delta y, that is basically the cross section area. All right. So in a Cartesian frame of reference, actually, what you can have is x and this is y. So if this is a particle having delta x and delta y as the dimension and having the respective velocity v here, and this is u of this particular side. The other respective sides may have the velocity v plus the gradient in x direction of v is del v del x and delta x, and the other side parallel to x-axis, you can also write the velocity which will be u plus del u del y, that is in the y direction. You have this gradient, and this length is, change in length is delta y. So then if you do the treatment to find out the circulation, So these are the tangential component as well you can consider. And the length are delta x and delta y. And you have to take a sign convention here also. So you need to circulation means whether it is in this manner you are going to express or in this manner. Okay, so you have to choose between these two. So if we consider anti-clockwise positive direction of circulation, okay, that means for this particular closed loop, this should be the direction of the positive circulation part. So in that way, if you find out this circulation, it will be having two terms, as I was saying, del V del x minus del U del y and delta x delta y. So this bracketed term actually we know for a rotationality condition this term should be equals to 0. Okay, so this should be equals to 0 if the flow is irrotational, isn't it? So that if you are going to satisfy that, that means this circulation for irrotational flow, we can say that it will be 0. All right, and that is one conclusion or one type of consequence of this rotational flow. The other is we move forward to define the vorticity term, that is in terms of the circulation and per unit area, we can say. So it is actually defined as the circulation around this circuit, which is an infinitesimal size divided by the area. So which is denoted as omega, that is this y delta x delta y, which is nothing but this del v del x minus del u del y, isn't it? So this vorticity again for a rotational flow, this vorticity is going to be equals to 0 because this term should be equals to 0 for this irrotational flow. And this vorticity is actually a vector, which also denotes the angular rotation normal to the plane xy or normal to your screen, you can say. Okay, so it is a vector whose direction is normal to the plane of this particle or the infinitesimal element of fluid within which actually you have measured the circulation. Okay, so from this we also extend our discussion for a circular circuit or say for a circular streamline. You can also find out the this circulation term gamma. This is actually capital gamma, which is equals to, okay, so this is gamma, gamma in uppercase actually, and say caps. The lowercase of gamma is this, right? So this is the circulation for circular circuit. Okay. So if you are having a circular circuit like this, So this for that you can also find out, because here the tangential component will be if this is rotating with an angular velocity omega, so the tangential component will be omega r at a radius r. So that is my this tangential component, and the infinitesimal arc you can consider of d theta or delta theta, and then for delta theta tends to 0, it will be d theta. So r d theta will be this particular arc length, that is length dl, you can say, which is this one, that is r d theta. So this closed form integral will result gamma is equal to 2 pi omega r square, from which you have again gamma by pi r square is equal to 2 omega, right? So that is actually your vorticity. So vorticity is twice the angular velocity. From this particular form of a pattern of flow, we can have this relation also. I mean, in our kinematics, we had this definition of omega, angular velocity vector omega, and also vorticity is defined as twice of that. And from the perspective of circulation, we can also have this relation established. So that is about the circulation part and vorticity, how they are related. So that is about that, you can say, the prerequisite for before going into the basic flow patterns, right? So up to this, if you have gone through, if you are having any query, you can ask. Then we will look into the very quick look into the basic flow pattern. So if these parts are okay to you, we can move into the next part. Any query? I just tried to have a very summarized manner discussion of on this prerequisite part of potential flow. Main part actually now it will be the main basic flow and potential flow. So to understand that or to develop those, you need to have the knowledge of those functions: stream function, velocity, potential, vorticity, circulation, etc. So any query or
স্যার আপনি এর পরে একটা ছবি এঁকেছিলেন ওই ইরোটেশনাল ফ্লো এর জন্য, ইন প্লাস ওটা ইনভিজিট হবে, তো ওখানে মানে যে ফ্লুইড এলিমেন্টটা নিয়েছিলেন ওর উপরে ভেলোসিটিটাও ভি দিয়েছে, নিচেরটাও ভি, এবার তারপরে বলেছে ইরোটেশন। এবার আপনার মানে কি বলবো, ইনভিজিটের জন্য আমি মানে রোটেশনটা হবে না এটাও বুঝতে পারছি, কিন্তু মানে দুটো পয়েন্টে যে ভেলোসিটি উপর আর নিচেরটা সেমই হওয়া, এরকম কি ব্যাপার আছে কোনো? মানে আমার যদি দুটো সেম মানে কি বলবো রেটে যদি ডিফর্মড হয়, তাহলে তো আমি বলতে পারি ওটা ইরোটেশনাল।
Yes. This is just one example. তুমি এটার কথা বলছো। Actually, you have correctly pointed out. I mean, this is just এরকম এই ছবিটার কথা বলছো। এটা দুটো সাইডেরই ভেলোসিটি সেম, ইউ, আর y কম্পোনেন্টটা হচ্ছে v, এদিকের সাইডটাতে হচ্ছে v। এই তো ছিল, রাইট? তো এখানে
মানে এটা জেনারেল কিছু নয় আর কি।
for irrotational flow, you can denote this as a general case because what you are saying যে যদি দুদিকে একই রকম ডিফরমেশন হয়, যদি দুদিকে একই রকম ডিফরমেশন হয় তাহলে যেটা আমি আগের দিন কিছুটা ডিসকাস করছিলাম, তাহলে তোমার ওই এটা ইট উইল বি ডিফরমেশন, পিওর ডিফরমেশন, বাট নট আ রোটেশন। ইয়েস, অফকোর্স তুমি বলতে পারো, কিন্তু এখানে আমরা যদি সার্কুলেশন পয়েন্ট অফ ভিউ থেকে দেখি, সার্কুলেশনের পয়েন্ট অফ ভিউ থেকে দেখতে গেলে তোমাকে কিন্তু একটা ক্লোজ কার্ভ তৈরি করতে হবে বা ক্লোজ এনক্লোজারের মধ্যে করতে হবে, যেটা তোমার আলটিমেটলি এইরকম একটা চেহারাই নেবে, এবং যদি সেটা ডিফরমেশনও হয় অ্যাট দ্যাট পার্টিকুলার পয়েন্ট অফ টাইম ইনস্ট্যান্স, অ্যাকচুয়ালি তোমার ভেলোসিটি গুলো যদি এখানে কম্পোনেন্ট থেকে থাকে, মানে হোয়াট ইউ মিন টু সে ইজ যে তোমার এদিকে ভি আর এদিকে হয়তো ভি প্লাস ডেল ভি
del x into
ডেল এক্স, ঠিক আছে, ডেল্টা এক্স থাকলো, এখানে তোমার ইউ প্লাস ডেল ইউ ডেল ওয়াই, ডেল্টা ওয়াই থাকলো, যেখানে তোমার del v del x is equal to minus del u del y or vice versa হতে পারে। Okay, and also delta x and delta y should be same, so that তোমার এখানে তুমি যদি এই এক্সারসাইজটা করো তাহলে এই রোটেশনাল ফ্লো এর জন্য সার্কুলেশন জিরো হতে গেলে যে কন্ডিশনটা আসবে সেটা আবার ঘুরে ফিরে এই জায়গাটাতেই ফিরে আসবে, del v del x minus del u del y is equal to 0, যেটা আমরা জেনারেল কেসে করেছি। এখানে যেটা দেখানোর চেষ্টা করা হয়েছে সেটা হচ্ছে যে আগের দিন একজন সম্ভবত যেটা আমরা নিয়ে ডিসকাস করেছিলাম যে রোটেশনাল ফ্লো এর অ্যাজাম্পশন তার নিয়ে এই del v del x minus del u del y নিয়ে, এখানে ফিজিক্যালি যেটা থেকে অ্যাকচুয়ালি এই কনক্লুশনটা এসছে যে ইনভিজিট ফ্লো ইজ এসেনশিয়ালি অর ইরোটেশনাল। কারণ কি না, আমার একটা যে কোনো জিনিসকে রোটেট করাতে গেলে হোয়াট আই নিড, I mean now actually it is not from the kinematic point of view, rather from the dynamics point of view, how we can achieve a rotation. The moment you want to have a rotation, you need to have a shear stress that will generate a torque about a certain point, about which, I mean, if the axis is passing through that point, so about that axis you will be having a rotation of the element under consideration. Right? So you need to have a stress. I mean, for a fluid element, this the source of this torque could be due to the presence of shear stress, thereby shear force, and that will actually result in the torque. So the moment you are having a fluid which is inviscid, okay, so where from then the shear stress will evolve? You are having a inviscid flow, because the reason of shear stress in a fluid is due to viscosity. So if you do not have a viscosity at all, you do not have any kind of shear stress. Whether or not. So from there now, if you relate to this figure where we have this, I mean now if you do not have a shear stress existing, basically যেটা আমি এখন মুছে দিলাম, that term is due to this shear stress, তাই তো? Because this del u del y তার সাথে যদি আমি mu multiply করি, we are actually recalling Newton's law of viscosity. এই তো আমাদের এটাই তো নিউটনস ল অফ ভিসকসিটি বলে, মিউ ডিইউ ডিওয়াই ছিল, এখানে আমি এটাকে del u del y ফর্মে লিখতে পারি। সো দিস এক্সিস্টেন্স অফ দ্য gradient, in other way actually, or in other words we can say that it is this existence of del u del y is due to the property mu, which will result the shear stress or tangential stress. So if this mu is not there, you will not have any tau. And if you do not have any tau, you do not have any del u del y. So the element
যদি মানে এরকম কোন একটা মানে আমার বডি ফোর্স ফিল্ড থাকলো, তো সেটা দিয়েও তো আমি একটা গ্রেডিয়েন্ট আনতে পারি আর
রাইট। এখানে পার্সপেক্টিভটা তো আমি প্রথমে বলার সময় বললাম যে এখানে ডিসকাশনের পার্সপেক্টিভটা হচ্ছে ইনভিজিড ফ্লো, ওকে, is necessarily irrotational. Irrotational. This is the statement actually. All right. So in order to, establish this statement, in the moment you are saying the flow is inviscid, it should be irrotational if there is no other, because here we do not have any other existence of force apart from the pressure force as the surface force. There is no other body force. Definitely you may have other kind of body force term existing, but for example, if the plane under consideration is not a horizontal plane, if it becomes a vertical plane, then of course you need to consider the weight of the fluid volume itself. So that is the body force term. But due to that body force term, can you expect a kind of rotation? কারণ রোটেশনের জন্য এসেন্সিয়ালি যেটা দরকার সেটা হচ্ছে আমার একটা ট্যানজেন্সিয়াল ফোর্স, যেটা সারফেস ফোর্স হতে হবে। ঠিক আছে, তো সেই সারফেস ফোর্সটা আমার যদি ভিসকাস ফ্লো হয় তাহলেই এই ডিফর্মেশন রিলেটেড কারণে আমার রোটেশন হতে পারে। অর এলস তুমি যদি বাই এনি এক্সটার্নাল ফোর্স তুমি যদি একটা ফ্লুইড ভলিউমকে ঘোরাও, সেটা একটা রোটেশনাল হবে। বাট দ্যাট ইজ নট, দ্যাট ইজ নট আওয়ার কনসিডারেশন। সেই যে রোটেশনটা হবে তার সাথে ডিফর্মেশনটাও জুড়ে থাকবে। সো in absence of any external means, the possibility of rotation will be due to viscosity. এটা কি আমরা বলতে পারি? So if that is the case, if this you agree, then if I say the flow is inviscid, then it will be necessarily irrotational. আমার কোন রোটেশন থাকতেই পারে না যদি আমার ইনভিজিড ফ্লো হয়। কিন্তু এখানে ইমপ্লিসিট হচ্ছে যে আমি কোনো এক্সটার্নাল মিনস দিয়ে ঘোরাচ্ছি না, তাহলে বডিটা আমার অ্যাজ এ হোল ইরোটেশনাল ফর্মে মুভ করতে পারে। ট্র্যাজেক্টরিটা ট্র্যাজেক্টরিটা সার্কুলারও হতে পারে, কিন্তু বডিটা নিজের অ্যাক্সিসের অ্যাবাউটে কোনো রোটেশন হবে না, অ্যাজ ইফ দ্য বডি ইজ আ রিজিড বডি অর আ সলিড, সেইভাবে মুভ করছে। তো সেইটাকে রিপ্রেজেন্ট করছে আমাদের এই ছবিটা। এবং এখানে যদি আমরা সার্কুলেশনটা ইভ্যালুয়েট করি, যেটা অ্যাকচুয়ালি দেখানো হয়েছে, কিপিং ইন মাইন্ড দ্য সাইন কনভেনশন, it comes to be equals to 0 এই সিচুয়েশন। ওকে দেবজিৎ, এটা কি পরিষ্কার হয়েছে?
হ্যাঁ স্যার, হ্যাঁ স্যার।
ওকে, সো আফটার দ্যাট আর কারোর কোনো এই সংক্রান্ত কিছু, এই রিলেটেড এনি কোয়ারি যদি না থাকে, দেন আমরা তারপরে যে বেসিক প্যাটার্ন। আবার দেবজিতের কি হয়েছে বলো? তোমার ভয়েস
প্রাথমিকভাবে যদি
ব্রেক,
শুনতে পাচ্ছেন?
হ্যাঁ শুনতে পাচ্ছি, তোমার ঘর ঘর করে। বলো বলো বলো।
ও স্যার নেটটা একটু ওই একদম ফার্স্টে একটা ক্রাইটেরিয়া ধরেছিলাম, ওখানে আর কি ইনভিজিট ফ্লোর জন্য দেখানো হয়েছিল যে লাপ্লাসিয়ান অফ ভেলোসিটি ভেক্টর ইজ 0। তো এবার ইনভিজিট ফ্লো কি সঙ্গে কি আপনি ইনকম্প্রেসিবলটাকেও ধরে নিয়েছেন, কারণ কি ওটা ছাড়া তো মনে হবে না এটা।
Yeah, of course, of course. কারণ দেখো, actually we are satisfying the continuity equation. And this 2D continuity equation is del u del x plus del b del y is equal to 0. What type of continuity equation is this?
স্যার ইনকম্প্রেসিবল, কারণ ওখানে ডেল রো ডেল টিটা নেই।
Right. Then it is inherent. Incompressibility is inherent in the expression of continuity equation that we are using here. Otherwise, you cannot write del u del x plus del b del y is equal to 0. There will be a row term. Right? Na? মানে এখানে কোথাও স্টেডি না আনস্টেডি সেটা তো আমার I don't need to mention whether the flow is steady or unsteady. If it is an incompressible flow, always you will be having the form of continuity equation like that. Del u del x plus del b del y is equal to 0 if it is a 2D flow. 3D হলে আর একটা extra term ঢুকবে del w del z, that much. But there won't be any row term. তো সেটা তো মানে ইমপ্লিসিট না, যে মুহূর্তে ইউ আর ইউজিং দিস ফর্ম অফ কন্টিনিউটি ইকুয়েশন। ঠিক আছে?
হ্যাঁ স্যার, ঠিক আছে।
আর any questions from others? Okay, so we can now continue to the this basic flow patterns, and I think this fundamental part, if it is clear to you, then actually the rest of the potential flow is very much mathematical. But I mean, it is not only mathematics that is being exercised for this potential flow analysis. You need to understand the physical significance as well. But the treatments are purely from mathematical framework. Like, the uniform flow pattern, or it is also known as the rectilinear flow pattern, where we have a velocity which is uniform along one axis. Here we have taken as y-axis along which the velocity is uniform, and only one component of velocity we are having, that is our x component velocity. So the velocity vector actually is defined as I cap u naught, because this is uniform along y-axis, so it is a constant along y-axis. So I cap u naught, and there is no this j component or y component of velocity. So it's a very simple mathematical exercise. Knowing the definition of u and v in terms of psi and phi, one can obtain one can solve for getting the expression of psi and phi respectively. So, and that we obtain for uniform flow. For this basic flow patterns, we have first the uniform flow in terms of this stream function psi. It is minus u naught y, and the velocity potential phi, it is actually minus u naught x, right? I think it is very straightforward, and graphically this flow pattern is nothing but we can express these are the graphical representation, or you can also say the streamlines. These are the streamlines. So that is why it is also known as rectangle. So it's a linear, straight, parallel lines representing your u naught, and this is your x-axis, and this is your y-axis. So we are having these particular streamlines. U naught is the velocity, which is not changing along y direction. All right, so this is the uniform flow, and which is physically, I mean, you can also correlate, I mean, away from the boundary. If you are having a steady velocity, fully developed velocity field, this is quite similar to the one that we are representing here as uniform flow. But the second one, is it clear to everybody? I think, do you have any query?
Yes, sir. Clear.
Okay.
Yes, sir.
Yeah, here actually, I mean, you can also represent the flow network. And these are the streamlines I have drawn perpendicular to this, just like the grid that you can see, that will be the flow network on the background. So that is actually the flow network for rectilinear flow, where the perpendicular lines are the equipotential lines. The second one, basic flow pattern, is a source or a sink. This is rather, you can say, a kind of hypothetical pattern, source or sink. And both are same, only the direction is different. I mean, it is just the reverse direction. So here, I mean, we are actually talking about line source or line sink. That means if you are having a, say, a cylinder, a closed cylinder within which you are having a pressurized fluid. Now, along this circumference, if you have small holes, and all are being pricked at the same time, then what will happen? Due to the pressure inside, you can observe that flow coming out from all the holes in radial direction outwards because of the inbuilt pressure of the cylinder. I mean, inside the cylinder. Inside the cylinder, you are having a pressurized fluid. Just to give some physical sense of what is actually meant by source. So, so the fluid will come out in radial direction from all the holes in all directions. So that is being defined in a mathematical framework as a point from which fluid comes out uniformly in all directions. So physically, you cannot have within a 360-degree angular extent n number of or infinite number of holes, right? So there will be finite number of holes, but mathematically it is possible. So, and also you are having, I mean, this is a finite diameter cylinder, maybe diameter of a radius r. So if I decrease the radius of the cylinder, keeping the pressure of the fluid same, so as you go in, I mean, inward, that means if you decrease the radius, and then you may observe that the magnitude of the velocity will be more, right? So it means that as you go towards the center, your velocity will go on increasing, and at center there is a situation of what we call a singularity or point of no solution. That means at the center you are going to have the situation undefined. Okay, so that is the typical phenomena of source flow. Okay, so basically the way it is being represented is at a particular cross section. at a particular cross section, I mean perpendicular to the, so the way it is being represented is like this. You are having all radial lines with yeah, okay, with a discontinuity at the center. Okay, so just as a representation, I am drawing only these few lines. And so essentially for a source flow, first of all, the flow is radially outward. That means you are only going to have one component of velocity, that is the radial component. But before that, actually, here there is a change of stance, you can say, in terms of the choice of the reference frame. In the uniform flow, it was the Cartesian frame of reference, and typically before that, whatever we did with actually, we use the Cartesian frame of reference. But here, for the first time, while defining this source flow or sink, we actually use the polar or cylindrical frame of reference, where we are having r and theta. Again, because of 2D, the third dimension is the z, or the perpendicular to your screen of the plane. So at a particular section where you can have this r and theta component of velocity, so that it will be looking like a point. But if you go inside or come upward perpendicular to the plane, you can have these several numbers of these circles possible, or this radially outward flow possible. Basically, I'm talking about, instead of this this particular location, you can also have a number of holes here, right? So this is my z direction, you can say. This is r and theta. So r theta and z, where for 2D situation we are only having r theta. Okay, so coming back to this, so here we are having the first important part is that the frame of reference has been changed from Cartesian to cylindrical, and then we are having for this typical definition of flow, we are only having the radial component of velocity, and that is being defined in terms of a term which we have seen. It is the source strength. It is basically again here some kind of physical sense is given. It is the discharge or volume flow rate per unit source length. So if you are having an unity length and the circumference is 2 pi r, so 2 pi r into 1, this is basically the cross section. And if you have the knowledge of the radial component, because here we are only having the radial component, that is VR, so you are having the volume flow rate. Okay, and that is basically defined as M in our text. So it is actually M as equals to 2 pi r into 1 is the unity length and the radial component of velocity VR. Okay, so from which we get the expression of VR as M by 2 pi r. Okay, so this is the definition of or the expression of velocity for a source flow in terms of the source strength M, and we are having V theta equals to 0. Okay, so just can you give me 5 minutes time for a break? I'll be back in 5 minutes. Okay.
Okay, sir. Okay, sir.
So this is the way we have started to define the source flow, and accordingly you can have the definition of stream function and velocity potential. The relations for stream function and velocity potential with respect to the radial and tangential component of velocity, that is VR and V theta, are VR is equal to minus 1 by R del psi del theta, as it is. One can have the coordinate transformation and it can be shown. So I think that you can check. And in terms of the tangential component, it is V theta equals to del psi del R. And similarly, the velocity potentials can be defined as VR equals to minus del phi del R. And V theta
1 by del psi del R.
1 by R del psi del theta is VR.
Yes.
VR is equal to 1 by R minus 1 by R del psi del theta, and V theta in terms of stream function can be written as del psi del R. Okay, and in terms of velocity potential, it will be VR equals to you can write as minus del phi del R, and V theta is equal to minus 1 by R del phi del theta. So you can, it is easy to remember when it is R actually, the radial component for in terms of psi, the partial differential will be del psi del theta. And it is just the reverse for the expression in terms of velocity potential. Okay, so here you can get the expression of stream function psi as minus m by 2 pi theta, and this velocity potential as minus m by 2 pi log R. And this is actually resulting the streamlines which are being shown here. If you start this as a reference where psi equals to 0, so it will be psi 1, psi 2, like that. And velocity potential lines or the equipotential lines will be concentric circles like this. Okay.
স্যার ওই যে ইন্টিগ্রেশন কনস্ট্যান্ট আর ওটা কি হয়ে গেল, যার কোনো এফেক্ট নেই ওই স্ট্রাকচার ভেলোসিটির উপর, প্রেসারের উপর বলে নাকি?
কি বলছো আরেকবার বলো? কনস্ট্যান্টটা ভেলোসিটি
ওই যে ওটা কোনো মানে বেসিক স্ট্রাকচার আর ভেলোসিটি আর প্রেসারের উপর কোনো এফেক্ট নেই বলে ওই C1 C2 টা কি হয়ে গেল? মানে
হ্যাঁ, এখানে অ্যাকচুয়ালি আমি আগেও যেটা বলেছি, যখন স্ট্রিম ফাংশন ভেলোসিটি পোটেনশিয়ালের বেসিক ডেফিনেশনের জায়গাতে, যে যেখানে বেসিক্যালি তোমার কি হবে না, সাই উইল বি অ্যাকচুয়ালি তুমি যেটা বলছো যে ইট উইল বি প্লাস সাম C1, or in case of phi it will be plus some constant C2. All right, so you can choose this your own datum where you can set this C1 C2 equals to 0. Okay, তার রেসপেক্টে তুমি এই ভ্যালুগুলো psi 1 psi 2 psi 3 সেগুলো সেট করছো। আমি যেখানে psi equals to 0 লিখছি, যেটা লিখলাম এখানে, সেটা সে ওখানে হয়তো তোমার psi এর ভ্যালুটা অ্যাকচুয়ালি একটা তোমার সে 10, ঠিক আছে? তো সেটা যদি তোমার জানা থাকে, ইট ইজ জাস্ট আ স্কেলিং, ইউ ক্যান সে, বিকজ ইট ইজ অ্যান অ্যাডিটিভ টার্ম। লাইক ওয়ান ভেরি কমন অ্যানালজি আই ক্যান give you, like the gauge pressure. What is gauge pressure? You know?
Yes, sir.
What is gauge pressure? কাকে বলে?
যেটা হচ্ছে প্রেসারটা রিলেটিভ টু অ্যাটমসফেরিক প্রেসার।
Right, pressure related to atmosphere. So, gauge pressure equals to 0. What does it mean? Is it actually zero pressure?
Open to atmosphere.
If I say in a container here, you are having a pressure equals to 0 within bracket gauge, okay, or GAG gauge, both are. So, does it mean that within this container the pressure is 0?
No.
No.
No, sir. No.
It is actually atmosphere, right? So that means the absolute pressure is P equals to 0 plus P atmosphere. So this is analogous to our, CO. Getting my point? It is just the way you are representing psi as in a relative manner. Okay, so that is why you need not bother. We need not bother about C1, C2. In actual case, of course, because this entire exercise is as I said, is a kind of hypothetical mathematical exercise, which is having a certain correlation with some physical situation, but it is not exactly the representation of the physical phenomena. Okay, but so here you can make this constant equals to 0 as if you are choosing a particular reference where this C1 and C2 becomes equals to 0. So that is your starting point of defining the flow field maybe. We can do that as we did for the case of representing pressure. বুঝতে পারলাম?
Yes, sir.
Okay. So in a similar manner, sink is just the reverse of that. So in case of a sink, it is the same expression, only the direction is reverse. So in a sink, actually, flow from all direction is actually going to converge to a point, and you are having immediately displacement of those volume of flow which is being accumulated at the center, hypothetically. Okay. Otherwise, how can you give space for the flow? So basically, in case of a sink, it is just this direction towards the center instead of coming out from the center. So this is the representation of the sink. I have drawn, this line for sink and red for source. So essentially, in terms of the representation of stream function and velocity potential, it will remain same. Only thing is that we need to define sink as psi equals to m by 2 pi theta and psi equals to phi equals to the velocity potential equals to plus m by 2 pi ln r. Every other things remain same. Again, here also we have the singularity at the center. Okay. And then the vortex flow, rotational vortex. So that is another fundamental flow pattern. So I think we are having 5 minutes time left. So it's a very quick description that I'm giving to you. Vortex and the source sink is just, you can say, a complementary set. You can, because here in case of a sink or source, the stream functions are radial, and the velocity potential, the potential lines are concentric circles. In case of vortex flow, the representation is just the reverse. The streamlines will be concentric circles, and the equipotential lines will be radial lines. I mean, radial, outwards. According to the definition of stream function and velocity potential, if you have seen, it is just the same representation, but given to or basically attributed to different functions. In case of vortex, flow rotational vortex or free vortex, my definition of psi is circulation over 2 pi. So here basically in terms of circulation it is being defined, and the vortex strength also is denoted in terms of that gamma. Okay, so here psi is gamma by 2 pi ln r, and here actually, I mean, that C1, the value of constant, is being evaluated at certain critical radius, you can say, because otherwise you cannot define it for a general situation. So psi is being defined as gamma by 2 pi ln r over r naught. It is some radius where you are having stream function equals to 0, denoted as r naught. Okay, so velocity potential is being obtained as phi equals to minus gamma by 2 pi theta, which is my stream function for a source flow. So accordingly, we obtain the flow net for a vortex flow. Okay, so that is basically our basic patterns of flow. So there are 3 basic patterns that we dealt with. That is vortex flow. There are 2 types of vortex flow, free and force. Essentially, it is the free vortex flow, which is due to irrotational flow. Okay. So next day we will be discussing about the combinations. And before ending today's meet, let me get the feedback of your problem solving of the first chapter, that is viscous incompressible flow. What is the status? Have you done all the problems?
Yes, sir.
Yes, sir.
All solved?
Sir, দুটো বাকি আছে লাস্টে।
স্যার ওই প্রবলেমস গুলো সলভ করতে গিয়ে কয়েকটা বেসিক প্রবলেম আসছিল, যেমন ওই কলার বিয়ারিং, তারপরে ওই ড্যাশবোর্ড, এগুলোর মানে থিওরিটা পাচ্ছিলাম না।
আচ্ছা আচ্ছা,
তো বেসিক্যালি হয়েছে
আমি আমার একটা প্রথম, ঠিক আছে, সেটা তো ওকে, দ্যাট ইজ নোটেড। আই মিন ড্যাশবোর্ড, কলার বিয়ারিং, মানে জিনিসগুলো কিরকম দেখতে, খায় না মাথা দেয়, সেই ব্যাপারটা।
হ্যাঁ স্যার, এগুলো একটু প্রবলেম হচ্ছে।
ঠিক আছে, এটা তো একটা আন্ডারস্ট্যান্ডিং এর জায়গা।
আগের প্রবলেমটা এরকম একটা ছিল কলার।
আচ্ছা, ঠিক আছে, কলার বিয়ারিং, ড্যাশবোর্ড, এগুলো আমরা একটু ডিসকাস করে নিতে পারি। আর রিগার্ডিং মানে সলভিং, মানে সবকটা প্রবলেম সলভ করা গেছে।
হ্যাঁ স্যার, হয়ে গেছে। এবারে কয়েকটাতে ওই অ্যান্সারের একটু প্রবলেম হচ্ছিল, যেমন ফার্স্ট যে প্রবলেমটা, ওখানটা স্যার ওই ওয়াল শিয়ার স্ট্রেস বার করতে গিয়ে 3টে ডিফারেন্ট শিয়ার স্ট্রেস আসছিল 3টে কন্ডিশনে। স্যার আপনি যদি প্রবলেমটা খোলেন তাহলে বলতে পারি আর কি, মানে ওই পিরিয়ডটা।
আজকে আর হবে না, আজকে 4টে বেজে গেছে। আমি একটা ডেট আমি বুঝে নিতে চাইছি যে একটা ফুল সেশন প্রবলেম সলভিং এর জন্য আদৌ রাখার দরকার আছে কিনা রিগার্ডিং ভিসকাস ইনকম্প্রেসিবল ফ্লো। আমি যতটুকু পাচ্ছি তাতে হয়তো খুব বেশি হলে 15 মিনিটের একটা সেশন হলেই বা আধ ঘন্টা এট দ্য মোস্ট একটা করলেই হয়তো হয়ে যাবে বলে মনে হচ্ছে।
হ্যাঁ স্যার, দুটোকে 3টে অঙ্ক দেখিয়ে।
মানে একটা হচ্ছে প্রবলেম 1 বলছো?
হ্যাঁ, প্রবলেম 1 স্যার ওই ওয়াল শিয়ার স্ট্রেস, আর ওই পরে ওইখান থেকে ওই কলার বিয়ারিং, ওই বিয়ারিং এর জায়গা থেকে একটা কি দুটো অঙ্ক মনে ছিল যেগুলো একটু সমস্যা হচ্ছে।
আচ্ছা, সেইটা কোন প্রবলেম একটু বলে দাও।
যে লাস্টে একটা ফুটস্টেপ বেয়ারিং ছিল ওটা।
হ্যাঁ, ফুটস্টেপ বিয়ারিং এর একটা ছিল, ওটার অ্যানসারটা মেন ছিল না, একদম লাস্টে 14 প্রবলেম সম্ভবত এটা, তাই তো? 14 প্রবলেমটা ওটার অ্যানসার মেলেনি ফুটস্টেপের। আর 10-এরটা তো তুই আমাকে দিলি, কিন্তু ওর থিওরিটা আমি নিজে ঠিক বুঝতে পারিনি।
হ্যাঁ,
ওটা ড্যাশবোর্ড বিয়ারিং এর।
ওটা ড্যাশবোর্ডে।
হ্যাঁ স্যার, ওটা ড্যাশবোর্ড। আসলে কলার বিয়ারিং এ ও ওই ইন্দ্রিল আমাকে আগের দিন ওই অঙ্কটা করে দিয়েছে, কিন্তু স্যার ও যেটা করেছে আর কি, মানে অ্যানসারটা মিলে গেছে, কিন্তু সেটা স্যার মানে নর্মাল জার্নাল বিয়ারিং এর কনসেপ্ট দিয়ে করেছে, কিন্তু কলার বিয়ারিং এ তো একটু ডিফারেন্ট হয় কনসেপ্টটা, আমি যতদূর জানি।
আচ্ছা, ঠিক আছে, তার মানে আমাদের এইগুলো একটু ডিসকাস করে নিলেই হবে, যা বুঝতে পারছি।
হ্যাঁ স্যার, এই কলার বিয়ারিং, ড্যাশবোর্ড আর ওই ওখান থেকে ওই ফুটস্টেপ, এই তিনটে বিয়ারিং একটু
কলার বিয়ারিং, ফুটস্টেপ বিয়ারিং, মানে প্রবলেম 1, 14 আর 10, এই তিনটে প্রবলেম একটু অ্যাড্রেস করার ব্যাপার আছে, বাকিগুলো সমস্যা হয়নি। ঠিক আছে, এটা টিপিক্যালি আমি ধরো নেক্সট উইকের মঙ্গলবারের ফার্স্টের একটা সেশন, তাহলে আমরা এই প্রবলেম নিয়ে একটু ডিসকাস করে ডাউটগুলো ক্লিয়ার করে দিতে পারবো।
ওকে স্যার,
ঠিক আছে। তো কালকে সেক্ষেত্রে আমার মনে হয় পোটেনশিয়াল ফ্লোতে আমরা কন্টিনিউ করি, যদি কালকে মধ্যে করে ফেলে যায় তাহলে আমরা পোটেনশিয়াল ফ্লো প্রবলেম শিট শুরু করে দিই। যা দেখছি যে তোমরা প্রবলেম শিটের ডিসকাস ইনকমপ্লিটেবল মোরালেস অ্যাটেম্পটেড, সো আমরা পোটেনশিয়াল ফ্লো যদি কভার করে ফেলতে পারি এই উইকেন্ডের মধ্যে, নেক্সট প্রবলেম শিটটা আমরা ফ্লোট করে দিতে পারবো। ওকে,
ইয়েস স্যার।
তো সেটা মানে সেটার জন্য যেটা দরকার সেটা হচ্ছে যে কম্বিনেশন অফ ফ্লো প্যাটার্ন, যেটা তার যে মেটেরিয়াল এবং ভিডিও এবং টেক্সট, সেটা একটুখানি দেখে নাও, একবার গো থ্রু করে নাও, তাহলে কালকে আমি যদি পারি 1 ঘন্টার মধ্যে পুরোটা কভার করে দেওয়ার চেষ্টা করব, তাহলে মঙ্গলবার দিনকে ওটা স্পিল ওভার করবো। ঠিক আছে?
ওকে স্যার।
হ্যাঁ, কিন্তু এই উইকেন্ডের মধ্যেই সেক্ষেত্রে চেষ্টা করবো যে পোটেনশিয়াল ফ্লোর প্রবলেম শিটটা আমরা ক্লাসরুমে দিয়ে দিতে, তাহলে তোমরা শুরু করে দিতে পারবে। ঠিক আছে, বাই টার্গেট যদি আমরা করি যে বাই পূজা ভ্যাকেশন, বিফোর পূজা ভ্যাকেশন অ্যাকচুয়ালি আমরা যদি দুটো বড় চ্যাপ্টার, মানে পোটেনশিয়াল ফ্লোটা বড় চ্যাপ্টার, বাউন্ডারি ল্যাব ফ্লো একটা বড় চ্যাপ্টার, বাউন্ডারি ফ্লো কিছুটা পার্ট যদি এগিয়ে রাখতে পারি, তাহলে অলমোস্ট মোর দ্যান মানে অ্যাবাউট 50% আমরা কভার করে নিতে পারবো বিফোর পূজা। তারপর পুজোর পরে বাকিটা হবে। সেটা মনে হয় কমফোর্টেবলি করে দেওয়া যাবে যদি তোমরা এই মানে যেগুলো সার্কুলেট করা হচ্ছে আগে থেকে সেইগুলো একটু দেখে রাখো, তাহলে এইখানে ডিসকাশনের জায়গাটা সময়টা কম লাগবে। ঠিক আছে, তো আজকে তাহলে এখানে শেষ করি। থ্যাংক ইউ ভেরি মাচ।
থ্যাংক ইউ স্যার।
থ্যাংক ইউ স্যার।
Thank you, sir.
থ্যাংক ইউ।